We often think of advanced AI as these, constantly self-improving systems. But a recent study found something quite interesting. Even sophisticated reasoning models can get trapped. If their initial thinking is flawed, just in the first small section, their performance can seriously drop, and self-correction doesn't always pull them out.
Right. It's quite striking how that bad start can really anchor them despite having these self-correction abilities built in. It definitely makes you wonder just how robust that reasoning process truly is.
And that's exactly what we're diving into today. We're looking at a paper called Learning from Peers in Reasoning Models. It tackles this head-on and suggests a solution inspired by something very human, learning from each other.
Yeah, this research isn't just pointing out a flaw, it's actively trying to find a better way by borrowing from human collaboration. So our aim today is to unpack their learning from peers, or LEAP method for you. We want to understand how it works, why it helps against this prefix dominance trap, and maybe what it tells us about AI reasoning itself. Think of this as your shortcut to understanding a really cutting-edge idea.
Okay, so let's first get a clearer picture of this prefix dominance trap. How did the researchers actually identify it?
Well, they set up a pretty neat experiment. They gave these large reasoning models, LRMs, problems to solve, but with a twist. They forced the models to start with fixed beginnings the first, say, 15% of the text taken from either correct solutions or incorrect ones for the same problem.
And then they just watched what happened.
Exactly. They measured the difference in success rates based on whether the model started with a good chunk of reasoning or a flawed one.
Was the difference noticeable?
Oh, absolutely. For models like QWQ32B, they saw that performance drop we mentioned nearly 20% just from starting with that incorrect 15% prefix. So the key thing for you to grasp is that even though the model could generate the rest of the response and potentially fix things, that bad start had a really strong negative pull.
Hmm. Suggests self-correction has its limits then.
It certainly seems that way, maybe more limits than we thought.
Okay, so a bad start can really throw them off track.
Yeah.
This is where learning from peers, or LEAP, comes in. Tell us about the core idea.
So the inspiration for LEAP comes straight from psychology, really. We know that talking things through with peers helps humans catch misunderstandings and correct their own thinking. LEAP tries to mimic this for AI models.
How does that work in practice?
Instead of having multiple AI reasoning paths work on a problem totally separately, which is a common technique called parallel inference, LEAP allows them to, well, talk to each other during the process.
They share information somehow.
Right. This happens periodically in what the paper calls leap blocks. Let's say every T tokens generated, these blocks kick in.
Okay, what happens inside a LEAP block?
Two main things. First, summarization. Each reasoning path, or peer, generates a short summary of its thinking up to that point. They keep these brief, under 256 tokens, so it doesn't slow things down too much.
These summaries aren't just generic.
No, and that's a clever part. They use different prompts to generate the summaries, like asking what's your current hypothesis, or what was the key step. The idea is to get varied perspectives on the reasoning, not just the same summary structure every time. You can find details on the triggers and templates in Appendix A of the paper.
Right, different angles. What's the second stage then?
The second stage is routing. These summaries get shared, but not with everyone. They're sent to a subset of the other peer paths. And the researchers tested 3 ways of deciding which summaries get sent where.
Okay, what were the routing strategies?
First was dispersed routing. This sends summaries that are the least similar to the receiving path's own summary. The goal here is to expose a path to potentially very different lines of thought, maybe shake it out of a rut. They measure similarity using something called normalized Levenshtein similarity.
Interesting, get a fresh perspective. What else?
Second, clustered routing. This is the opposite. It sends the most similar summaries. The thinking is maybe paths that are already alike are onto something good, so reinforcing that could be helpful.
Like finding collaborators who are on the same page.
Sort of, yeah. And the third was hybrid routing, which, as the name suggests, tries to get a bit of both, sending a mix of the most similar and the least similar summaries. Trying to get the best of both worlds, perhaps.
Okay, so paths summarize,
Yeah.
and then summaries are shared strategically based on similarity. How well did this actually work against that prefix dominance trap?
The results looked pretty good. LEAP significantly closed that performance gap caused by starting with bad prefixes. In some cases, it cut the gap by almost half, around 10 percentage points.
That's a big improvement. So just seeing what others are doing, even if some peers are also wrong, helps.
That seems to be the key idea. It forces each path to not just check its own work, but to also consider what its peers are doing. This makes it less likely to get stuck on its own flawed path and overlook a potentially correct direction another peer is exploring.
Mm-hmm.
And what's also interesting is that LEAP didn't only help when starting with bad prefixes, it also improved performance even when the model started with good prefixes.
Oh, why would that be?
It suggests LEAP helps catch more subtle errors that might pop up later in the reasoning, even if the start was okay. It's about ongoing refinement, not just initial correction.
Makes sense. It's a continuous check. Now, they didn't test this on easy problems, did they?
No, definitely not. They use some really tough benchmarks. AIME math competition problems from 2024 and 2025, AIMO 2025, and also GPQA Diamond, which is a very challenging general knowledge data set. These require some serious reasoning chops.
Right, serious stuff. What were the overall performance gains like?
They saw pretty consistent improvements across different models, from 7 billion to 32 billion parameters. Using LEAP generally boosted the pass at 1 accuracy. That's basically getting the answer right on the first try compared to the baseline where paths worked alone.
Any standout examples?
While the QWQ32B model using dispersed routing saw its average pass at 1 score jump by nearly 5 absolute points across these tough benchmarks. And remarkably, it actually outperformed a much larger model, DeepSeek R1671B, on 3 of the math datasets.
Wow, a 32B model beating a 67B model.
Yeah, with an average gain of about 3.3 points on those specific ones. They also mention a fine-tuned 7B model, LEAP T7B, matching another larger model, DeepSeek R1 Distill Keen 14B, on one of the AIME benchmarks. It really underscores how effective this peer interaction can be.
That's impressive scaling for a smaller model. Did the routing strategy matter much overall? You mentioned dispersed for QWQ32B.
Yes, it seemed to. Generally, dispersed and hybrid routing perform better than clustered routing.
So getting those different perspectives really was more beneficial than just reinforcing similar ideas.
That appears to be the case, yeah. Diversity of thought seems helpful even for AI models. They also noted strong results using a consensus measure, cons at n, which you can find in Appendix C.2.
Okay. What about the cost? Does all this summarizing and sharing mean it takes a lot longer or uses way more resources?
That's a crucial question. Interestingly, the study found LEAP doesn't necessarily generate significantly more tokens overall. Sometimes the average length of the successful reasoning path was even shorter with LEAP.
Shorter? How does that work?
Well, one related finding might explain it. They looked for what they called aha moments, points where a single path significantly revised or verified its own reasoning. LEAP path showed fewer of these moments.
So the peers are kind of doing some of that verification work collectively.
That's the interpretation. Getting insights from peers seems to reduce the need for each path to do quite as much intense individual reflection and self-correction.
Fascinating. Now, you mentioned a fine-tuned model, LEAP-T. What was the story there?
Right. The researchers observed that some of the base models, especially the smaller ones, weren't always great at following the instructions for summarization and reflection within the LEAP framework. They'd sometimes ignore them or not do them effectively.
So they needed specific training.
Exactly. They created the LEAP-T series 1.5B, 7B, and 14B parameter models by fine-tuning the base model specifically on generating these summaries and reflections using AIME math problems, teaching them how to be better peers, essentially.
Did that specialized training pay off?
It certainly seemed to. The LEAP-T models showed significant gains over the base models just using LEAP out of the box. For instance, LEAP-T 1.5B got about 4.45 points higher average pass at 1 than the standard 1.5B model with LEAP. And the 7B version also showed good efficiency when scaling up at test time.
So teaching them to collaborate makes the collaboration even better. Makes sense. The paper also dug into the specifics of how LEAP works, didn't it? The communication mechanics.
Yes, they did quite a bit of analysis there. They looked at communication frequency, how often the LEAP blocks occurred. More frequent communication, smaller t, generally led to slightly better performance, but
There's always a but.
it also used more tokens. So there's a trade-off between performance gain and computational cost.
Okay, more check-ins help a bit, but cost more. What about the amount of communication? How many peers should talk to each other?
They experimented with that too, varying the number of peer summaries each path received, the top K. Performance seemed to peak when receiving summaries from about 4 peers.
So not too few, not too many.
Right. Too few, and you don't get enough diverse input. Too many, and perhaps it becomes overwhelming or confusing for the model to integrate all the feedback. A sweet spot around K4.
And did it matter when the communication happened?
Yes, that was another interesting finding. They looked at the evolution of communication types and found that peer influence was most impactful in the early to middle stages of the reasoning process. Later on, paths seemed less likely to be swayed by peer summaries.
So getting that feedback early is more critical.
It appears so. They even tested a variant called leap in single communication, where paths only exchanged summaries once. Even that single early interaction provided significant benefits over the baseline of no communication at all.
Wow, one nudge can make a big difference. Okay, a really critical aspect is errors. How does Leap cope if many of the peers are actually wrong? Does the whole group just go off the rails?
This was one of the most surprising parts of the study for me, and probably for you listening too. The robustness test showed LEAP is remarkably tolerant to errors among peers.
Tolerant how?
It still outperformed the baseline model with no communication, even when a large fraction of the peer paths it was interacting with were generating incorrect reasoning.
Really?
Yes, and get this. In one setup, they started LEAP with no correct initial prefixes among its peers, while the baseline did have correct prefixes. Even then, LEAP eventually outperformed the baseline.
That's incredible. So even surrounded by bad ideas, it can still find its way.
It suggests the models have a strong enough self-verification ability to sort of filter the noise and extract useful signals, even from flawed peer reasoning. That resilience is quite something.
Definitely. Does this hold up across different problem difficulties?
Yes. They analyze performance on AIME 2024 problems broken down by difficulty. LEAP showed consistent accuracy improvements across easy, medium, hard, and even very hard problems.
Even ones where the baseline completely failed.
Right. On the very hard questions where the baseline often scored 0, LEAP could still find correct answers. And often it did so using fewer tokens than the baseline attempts.
More accurate and potentially more efficient on the hardest problems. Okay, lastly, they did some human checking too.
They did. They took a specific AIME problem and had humans evaluate the reasoning paths generated with and without LEAP. They saw a big jump in correct answers with LEAP, from 25% correct without it to 62.5% correct with it.
And they looked at how the answers changed.
Yes, crucially, they found many instances where an initially incorrect reasoning path was corrected after interacting with peers, the incorrect-correct category. And importantly, they saw basically no cases where a path that was already correct got derailed by interacting with peers.
Correct.
Incorrect.
So it helps fix errors, but doesn't tend to introduce new ones. That's good.
It seems that way. The appendix case studies also offer more color, showing, for example, smaller models sometimes struggling with the summarization task, or certain RL-trained models being perhaps too confident and resistant to peer input. But they also show clear success cases where peer interaction directly led to fixing errors or completing partial reasoning.
Okay, so wrapping this up for our listeners, we've seen this prefix dominance trap is a genuine hurdle for AI reasoning. But this LEAP method, inspired by human peer learning, seems like a really powerful way to counter it by letting reasoning paths collaborate and catch errors.
And the fine-tuned LEAP team models show that explicitly training for this kind of interaction boosts the benefits even more.
For me, the real aha moment here is that robustness. The fact that LEAP works well even with noisy or incorrect peers and across all difficulty levels kind of challenges assumptions about how perfect collaboration needs to be for AI.
Absolutely. It suggests these models might be better at learning from imperfect interaction than we might have thought.
It really makes you think, doesn't it?
Yeah.
Could these ideas, peer learning, collaborative error correction, apply beyond AI? Maybe to how humans work together on complex problems. Could we design better systems for our own collective intelligence using similar principles?
That's a great thought to leave listeners with, and the paper itself points towards future work, like using LEAP in reinforcement learning or having peers with different specialized skills or tools interact. So this is clearly an active and evolving area of research.